So I will talk about what WFIRST will do regarding proper motions. But I will talk, people are probably already sleepy, so I will try to make so that in terms of HST, what HST has done, what WFIRST would do, so that I'll go back and forth, go talk some science results, and then go to WFIRST again. So that's what the plan is anyway. So the WFIRST, the field of view, oops, sorry, okay, sorry. So the field of view of WFIRST in terms of HST, the Hubble field of view is this little thing. So this is more like 100 times the Hubble's field of view. So this is 90 times the ACS, the Advanced Camera for Survey, 200 times of the WFC3. So that's a single field, but also WFIRST will observe, of course, 10 such fields. So it will be really 1,000 times the field of Hubble. So that would be an enormous improvement. So to go a little more about what the plan is, so the integration time would be roughly 50 seconds or so. So this every field would be observed about 15 minutes in interval, and continuously for 72 days is the current plan now, right? So and it will probably, depending on how it goes, maybe 6 or 7 times it will observe during its lifetime. So the expected accuracies of the expected accuracies would be, so just to go by the formula, so the measurement uncertainty in the position of a point source would be given by the positional uncertainty is the full width half maximum divided by the signal to noise ratio of the point source. So if the full width half maximum is about 0.1 arc seconds, let's say if for a V of 20, J of about 17 or 18, there would be about 10,000 counts. That means signal to noise will be 100. So for this kind of source, per single epoch, you can have about 1 milliarc second of positional accuracy. So the 1 milliarc second, I wanted to demonstrate what 1 milliarc second is. So 1 milliarc second is, you are in Los Angeles, you put a US quarter in New York, and the width of that US quarter that you observe from here is 1 milliarc second. So, and that is the one that it will measure in, if an insect is moving from one end to the other of the US quarter, you are observing that from here. That's what it's per epoch, that's what its measurement accuracy would be. So why we are going to observe, what is the importance of measuring proper motions of the bulbs? So here, sorry, I'm keeping back again. So here, okay. Here is one where, this is the radial velocities, just the radial from the Brava measurement, the radial velocities. You hear the galactic longitude versus the velocity. So you see that there is the rotation curve, you can call it. So as you go from -10 to 5, the rotational velocity now flips over. So this is all that was known from radial velocity, the line of sight velocities. So there have been some work on actually measuring the proper motion of stars from ground and from space using different techniques. And these are mainly, so from Ogle 2, for example, a million stars proper motions were derived, the accuracies of about 1 to 3 milliarc seconds per year. On space-based observations, there have been also a number of studies, particularly the people who study globular clusters. The globular clusters, particularly towards the galactic bulbs, there are a few, and there they needed to separate out the globular cluster population from the bulbs population, and that is what they do through proper motions. So they have measured for that. That actually has given rise to the many sequences main sequences in a particular globular cluster. That has been a fantastic result within the past few years. So for that, there have been a lot of studies for proper motions. So there are pointed studies, but there are proper motions measured for those lines of sight. Then there is the Kauken and Rich. They did based on just WFIRST-2 data. They did some proper motions. And Stanek window, there is a poster outside on the proper motion measurements there. Then there are proper motions from microlensing follow-up observations. There are a few observations, few microlensing events have been followed up with HST, and for them also there are proper motion measurements. And then RV. And what I am going to talk mostly are based on some of my own programs, and how those are probably the best, I must say. Those are because these are the deepest observations so far, and also the maximum baseline of about 10 years. So those are probably the best proper motions available so far. So I want to talk a little bit about what those two programs are and give the results, and then go back to WFIRST again. So the first one, so this is again why we want to study the proper motions. There are a bit more on that. So the proper motions help you, as I told you, for example, for globular clusters, they wanted to separate out the bulge and the globular cluster population. At any, let's say, towards close to the Sagittarius window or Bardes window, there are about 10% of the stars, 10 to 15% of the stars are actually disk stars. So if you want to study the bulge population, you need to separate out the two, and that you can do through proper motions. Then for all the microlensed sources, for about 75% of the microlensed sources in the bulge, the location that it is in the bulge, you can confirm through, if you know the proper motions, for 75% of them, you can confirm, yes, indeed, it is in the bulge. We'll come to that, why it is. And then there are other projects like blue stragglers, initial mass function, white dwarfs, all that you can study. Okay. So I want to go to the first project, which is the SWIPS project, which will form the first epoch of the proper motion study. So I want to talk a little bit more about the SWIPS program itself. By the way, when do I? So okay, good, thank you, thanks. That's very useful. Okay, so so the SWIPS program was to actually look for transiting planets in the galactic bulge. So what we did was, so this was many years ago when there were before Kepler. So we wanted to know what the detect transiting planets in the bulge itself. In fact, this is the only program which has detected clearly detected the transit objects in the galactic bulge itself. So these are the farthest planets detected so far. So our idea was to see what the planet frequency would be in a completely different population. So we monitored this particular, the SWIPS field. SWIPS stands for Sagittarius Window Eclipsing Extrasolar Planet Search. So we monitored this continuously for 7 days with HST. And let's zoom in over this particular field. So the SWIPS field, you saw that. And now let's zoom in. Here now you see this is now the digitized sky survey. So this is the digitized sky survey. It's extremely crowded here now. And now you see the HST image. So the HST image is, so we are zooming into the HST image. With HST, of course, you also resolve the stars. And so, sorry, just like the previous one, I am also showing a simulation. So, and you see the planet. So, okay, so this is the field that we monitored. So this is 3 by 3 arc seconds, 3 by 3 arc minutes. And there are about 180,000 stars that we monitored. And so this is just about the deepest galactic field ever observed anywhere in the sky. And so this we had, so this is a movie which tells what the procedure we adopted actually in detecting our data reduction procedure. So what it shows is I have cut out a small field of that sweeps image. So this is that as we observed. And then you see here there are a lot of cosmic rays and all that. So after we subtract out the cosmic rays, how it looks. So here it looks as if nothing is changing now. So then after the cosmic rays that were actually subtracted out, that's shown here. And then HST itself actually has a breathing pattern. We correct for that breathing pattern through a convolution kernels, and that's so that a representation of that is shown here. And then what is shown here is we take the average of all these 250 observations and then subtract out this image. So the difference image is now shown here. You would see, now you see there are a couple of, actually I put a couple of stars which are actually changing by about 5%. So this is pretty clear cut. So then we choose the stars, and then we go over this the photometry and all that. Anyway, that's not the point here now. So let's go. Sorry. So we achieve by that. This is what you expect is from the Poisson characteristics. This is what you would expect, and we achieve pretty much the signal to noise is consistent with what you would expect from the Poisson noise. There are brighter stars. These are saturated stars where it is where we also do photometry, but there the accuracy is slightly lower. And then so these are, then we go through the different steps in fitting the transit light curve, and then we detect the planets. So So these are few planets that we discovered. So there are 16 planet candidates we discovered. 2 of them were actually confirmed through radial velocity. Most of them are actually too faint for radial velocity measurements, but 2 could be observed, and both of them were actually planets. So this is the first step in our proper motion measurements. The second step, now let's go to the second step, is through another program which I did, which is mainly to detect black holes. So since this is so I want to talk a little bit more on isolated black holes. Of course, this is also one of the main goals for WFIRST as well. So we know that every star which has a mass, which starts with a mass of more than 20 solar mass, ends up as a black hole. Now, there are theories. So out of these, so you should expect from stellar evolution theory, you expect about 100 million black holes in the galaxy from the evolution. And out of those 100 million, a large fraction of them are actually expected to be isolated, because first of all, 25% of the stars to start with are already single stars, right? So they end up as single. And then out of the ones that start as binary, then the close binaries, they merge. Okay, so that makes a single one. And then if there is a wide binary, then the kick velocity sometimes kicks the companion off, and so they end up again as single. So there should be lots of isolated black holes, but none has been actually detected within our galaxy so far unambiguously. So this microlensing provides a wonderful opportunity to actually detect. So we have a couple of programs. So to go a bit more, actually, so there are. Sorry, I'm seeing the wrong button. The black hole masses, so far as the observations go, the masses of neutron stars in the black holes that have been discovered so far in our galaxy are all from binaries, right? X-ray binaries. And the masses of those come out to be about 8 ± 2 3 solar mass. Whereas the theoretical models predict that there should be a continuous distribution from 3 to 20 solar mass. Then the LIGO observations, those are about 10 to 30 solar mass. So there is a discrepancy between observation and theory. So if we detect and measure the masses of black holes, that potentially can solve this problem. And so microlensing is a absolutely fantastic way to actually measure the masses of these. So to give a little more introduction, so the mass of the lens, you have already, the theory has been discussed in detail, so I will not go into all details. But so if you observe say a light curve, then the mass of the lens depends on the time scale, the velocity, and the distance to the lens and the source. So it depends on the time scale, the velocity, and the distances. And the major uncertainty comes from the velocity. dE is what you measure. dl, sometimes you can measure the dl itself. The v is the most uncertain quantity. If you measure the astrometric shift, then an amplification at any given time in the light curve is a pure function of u, right? So now, if you measure the astrometric shift now depends only on this u and the Einstein ring radius. Okay? So if you measure delta, the astrometric shift, and you know the amplification as well, so that means you have already measured u. So that means if you measure astrometric shift, you know the Einstein ring radius. Okay? So the Einstein ring radius is now Re over dl. There is no time scale, doesn't come in at all here. Okay? So Einstein ring radius now depends only on the mass and the distances. You have got rid of the time scale, which was the most uncertain one. So now, if you so the distances, oftentimes, particularly for the long duration events, you can measure the distances through the microlensing parallax. And most of the time, you know the distance to the source, either from the most of the time it is in the bulge, but you can also plot it on the color magnitude diagram and say that yes, indeed, it's in the bulge. So you know the distances, and you know, so everything you know to get the mass. Not only the mass, but actually you have this is one method actually which tells you everything about the black hole. So you know. If you recall, we did not actually use in measuring the mass, we did not actually use the light curve at all. The time scale we did not use, right? So now we know the distance to the lens, the distance to the source, and the mass. And once you know the mass, then the time scale now gives you the velocity. So from the single method, you measure the distance to the source, distance to the distance to the black hole, the mass of the black hole, and the transverse velocity of the black hole as well. So this is what the idea is. So we have a HST program to actually 2 HST program to do this. We have detected lots of microlensing events, but we have not detected black hole signatures yet. So this is what we are doing. So we are monitoring these 16 fields. So there are approximately about 1.3 million stars, 1.7 million stars. I won't go through all this program in detail, but so for this program we are monitoring for 3 years, and those observations happen to be about 10 years later. So that gives a perfect baseline for proper motion studies. So I want to show here is, let's see if it plays. So this is actually not the 10-year baseline, but just three images taken within 1.5 years or so, and you can see the motion of the stars. So they are the galactic bulge with HST resolution. Look at any let's say here, you see the motion. Here you see the motion here. Well, here you see the motion. So everywhere, actually, every star is moving. This is just for 1.5 years, not even 10 years. So the stars are moving, and so to measure the proper motions is relatively straightforward. So this is, again, just for 2 years, the proper motion of a few measurements. So this is 22nd magnitude, this is 19th magnitude. So you see the straight line, those are the proper motions, and that's how we, so these are actually published a long time ago. So this is a perfect way actually to separate out the disk from the bulge. If you, if you plot, let's say, the disk stars and the bulge stars, so this is the color magnitude above the main sequence turnoff. So so that means these are all the bulge stars, and this is all disk stars. So see the color magnitude, it goes here. So the disk stars continue this way, whereas the color magnitude of the bulge turns over here, right? So this is all the bulge, this is all the disk. And if you plot the proper motions of those separately, then it turns out that, so this is the bulge, and this is the, so this red corresponds to this bulge, and the blue corresponds to the disk. So there is a clear separation between the two in both L and B. And if you plot the mu B versus mu L, then the disk stars fall on the right side, whereas the bulge stars fall on the right side, and the disk stars here. So you can say that if a microlensed source, for example, falls on this part, is unambiguous that it is actually a bulge source. So of course here the accuracies were not large enough, so the dispersion is a bit high. Actually, if you about 75% of the sources you can easily separate out from the disk from the bulge. So I want to give a couple of, depending on how much time it will permit, I'll give a couple of different science projects that can be done, that we have done, and more can be done. Then tell what with WFIRST what more you can do. So we discovered, for example, the blue stragglers just from the proper motion studies. What's a blue straggler? So the blue stragglers are the old stars which look like young stars. Okay? So which are made more luminous and hotter by this mass transfer. So in this the color magnitude diagram, they would be around the region where the young stars form. So there was a lot of debate that there are some few stars in the galactic bulge population, say, which look like young stars. So there was a thought that, okay, probably there is a lot of young population in the galactic bulge. We looked at those in detail, and it turns out that, so here, these ones, so this is a proper motion cleaned one now, and still there is a population of stars here which look like young stars now. Now, if we take those and we look at it in detail in color, they actually don't correspond to young stars. And then when we plot, so these are the positions of those candidate blue stragglers. And so these are these are, as I told earlier. So these are, either mass transfer is happening, or there is a stellar collision, and there is again so it's mainly because of mass transfer. And in such a scenario, you would expect a tidal distortion. Okay, and if that is the case, then the photometry should have a variation. Okay, and out of 42, 8 of them actually show that kind of signature. So it was pretty clear that only the ones that are only a small fraction are expected to be so close to show these tidal variations. So it was pretty clear that they are blue stragglers, and that put a rest that the bulge does not have a large population of young stars. So bulge formed pretty quickly and does not have a young population. Okay, so So what does this tell us about the bulge, which I already told you? So this implies that within the region of the Milky Way bulge, fewer than about 3.4% of the stars are young, pretty small number. We can never say zero, because, you know. Okay. So, and then there is another, we also discovered white dwarf population. So this is the color magnitude diagram. This is the clean sample. It means this is the color magnitude diagram of pure, this is these are the disk stars. And so the disk stars have this motion, and the bulge stars have this different motion. And here again, what I showed you before, the disk and the bulge. And there was a large population of blue stars. Okay, so these are, we took this as the candidate white dwarfs, and we measured those, and we investigated them in more detail. And then again, so if they are white dwarfs, you expect a fraction of them to be because of the binary nature, the EBVs, and which we found. So this was the white dwarf population, which was not known. We detected that. Then we also used the proper, so as I told you, the proper motion helps you in getting a pure bulge population. So so we used that to get a mass function of the pure bulge population. So the mass function comes out to be slightly different from the disk. So our mass function agrees. So far in the higher mass range, the mass function is similar to the disk, but in the lower mass range, actually it's slightly different from the disk population. So now, so with the proper motion measurements with the WFIRST, so here what we measured was more like 180,000, 200,000 stars. WFIRST will measure proper motions about 150 million stars of all spectral types, because it will go down to about, if I talk of V, it's more like 25. So that will go down to about M, spectral type of M, with an accuracy of roughly 0.3 milliarc seconds per year, similar to the Gaia accuracy. 0.3 milliarc second would correspond to roughly 4 kilometers per second per year. So this will allow you to do the bulge disk separation, which studies in great detail about the pure bulge population. You can study the present day kinematics of the bulge, the kinematics of the micro-lensed sources, because WFIRST will, of course, detect thousands of micro-lensing events. So the micro-lensed sources, the kinematics of those you can measure. This will also give you an initial guess on the time scale of the lens source separation. You see, if you have if you say the parallax, you find, through parallax, let's say, you find that the lens is at 2 kiloparsecs. So that means in the VB diagram where the position of that is. Okay? And now if you find the source to be well far away from that, then you can tell how long it would take, actually you can estimate how long it would take to separate the lens and the source. So that gives you an initial guess on what the time scale would be. And then of course you can combine them with the radial velocity to get the 3D kinematics, and many other follow-up studies. I'm sure people can do that. So I would like to end with just one suggestion for Scott in particular. So because Scott was I want to get his attention. So, but for this proper motion measurements, you need we know that the Gaia sensitivity is low, but so far as the black holes are concerned, if you observe only for 4 seasons, let's say, that's really not enough to, from my experience, it's not really enough to get the complete baseline. So you don't need a lot, but even if you can spend, let's say, 1 hour of observation every 5 to 10 days on the years that you do not observe, do not have the microlensing campaign, which would take less than 1 day per year, then that project can be success. And then, so I have 5 minutes still? Okay, so I'm almost done. So, and then so that, and it would be the same for both black hole as well as the proper motion studies. So, thank you. So I went through the whole calculation on the first slide. Okay, so you have 0.1 milliarc second full width half maximum. Divide by 1,000. So that means, so you have 0.1 milliarc second. Divide by, so that means you have 1 milliarc second. 1 milliarc second accuracy per year. So if you have 2.5 years, you have 0.4 microarc seconds. Per year, but you observe if you observe for 4 years, yes.
So what Jake is worried about is the systematics, which I think are.
Yeah, well, yeah. So I am scaling with HST. Okay, so you know we have done similar ones for WFIRST, and it's pretty much the same. So we do achieve the same 0.1 for WFIRST IR detector. I don't know whether WFIRST, the WFIRST detector, is very different or not. But if the performance is the same as our WFIRST IR detector, it would be the same.